So in general, if you have a quadratic equation in a variable, the variable is lambda, how many solutions does it have? And a cubic equation in lambda would have? And a quartic equation? So if you did this in 3 dimensions, you get a cubic equation in lambda when you looked at the determinant of the matrix equal to 0. And if you did it in 4 dimensions, you'd get a quartic equation. And if you did it in 5 dimensions, you get a quintic equation. That's why in 1, 2, and 3, in n dimensions, you usually get an n-degree polynomial in lambda. And an n-degree polynomial in lambda has n solutions, but these solutions don't all have to have real values. So do you know about solutions to quadratic? You can say they have 2 real solutions, or 1 real solution, or no real solutions. But they always have 2 solutions if you're allowing complex numbers. So sometimes they don't have real solutions, they have complex solutions. But under certain circumstances, you'll get real solutions. Okay. So now if we go through and we say, okay, procedure for solving eigenvalues and eigenvectors. So step 1, find the eigenvalues by solving the quadratic equation. And then for each solution, you get 2 solutions. For each solution, you go back to this equation, and you put that particular value in over here. So you go back to your basic equation over here, and you say, if I put in a particular one of the values for lambda that I found, I get a corresponding eigenvector solution. And if I put in the other, I get a different eigenvector solution. So you get pairs. For each eigenvalue, you get its corresponding eigenvector. So how can we do that? Here's an example you can work through. So a is 7 minus 2, 15 minus 4. We set up the quadratic equation. We factorize the quadratic equation. And we get 2 solutions, lambda equals 2 or lambda equals 1. If lambda is equal to 2, then we can set up this equation, which is equivalent to saying 5x minus 2y equals 0, or the second one is 15x minus 6y equals 0. Now here's exactly what I was talking about. You get 2 equations. But these 2 equations are the same equation. Because if you take this equation and multiply by 3, you get that equation. So whenever you do eigenvalue, eigenvector solutions, in 2 dimensions, there are 2 eigenvalues, and you look at the eigenvector for a particular eigenvalue, and you really only got one equation. And that equation allows you to express x in terms of y, or y in terms of x. So all you can solve for is the ratio. But that's all you need, because it's that ratio that defines the direction of the eigenvector. So you can choose arbitrarily x equal to 1, and then you'll find that y equals 5 upon 2. Now for the case lambda equals 1, we can go back to this equation, and we can say a minus lambda I, and we can calculate that matrix, and that will give us 2 equations. 6x minus 2y is equal to 15x minus 5y. You'll see if we multiply the top equation by 2.5, then we get the bottom equation. So again, there's only one equation, and when you solve that, if we choose x equal to 1, then y is equal to a third. So when lambda is equal to 1, the eigenvector can be written as 1 a third, and when lambda is equal to 2, the eigenvector can be written as 1 and 5 over 2. So here you come to this theorem, and this theorem is the reason why we're so interested in eigenvalues and eigenvectors. And it says, consider this model. Un plus 1 is equal to a times un. Then the solution can be expressed for any n in terms of the eigenvalue to the power n. And you get 2 eigenvalues and the corresponding eigenvectors. And so it's the first eigenvalue to the power n times its eigenvector, and the second eigenvalue to the power n times its eigenvector, multiplied by 2 arbitrary constants. Those 2 arbitrary constants are there because you've got to match up the initial conditions. So if I say that at time 0, this is equal to some initial vector, then lambda to the 0 is 1, and mu to the 0 is 1. So it means a times this vector plus b times this vector is equal to your initial condition, which gives you 2 equations and 2 unknowns. And again, to see how this works, you have to go through the calculations. Now, I'm not going to go through these calculations. You can just work through them yourself. But I've given you the basic idea. And the final idea to do with all this theory is that if you can express the solution in that general way, and you've got 2 eigenvalues, lambda and mu. Let's go back to that solution and see what happens. Let's write down this. Let's go back to the theorem with the solution. Let's say lambda is 2 and mu is 1. So we start off when n equals 1, we get 2 times v and we get 1 times v, and we multiply by that a and b. When n is 2, we get 2 squared, which is 4, and mu is 1 times 1, which is still 1. When n is 3, we get 2 cubed, which is 8, and 1 cubed, which is still 1. So the bigger one dominates and grows faster. Now this will be true if whichever one of these has bigger absolute value. When you raise it to a power, it'll proportionally get bigger and bigger and bigger compared to the other. And so what it means is the one that has the biggest absolute value, its eigenvector is going to dominate the direction of where the solution will go. And this basic theorem over here just expresses this idea that there's going to be a direction determined by one eigenvalue and a direction determined by the other, and the one that has the biggest eigenvalue will determine where the population will grow. So if we go back to the Impala problem over here, you can imagine that we found one of the eigenvectors over here. And this one that we found is the one that has the biggest eigenvalue because it's controlling where the solution goes to. So let's go back to the Impala model over here and calculate its eigenvector and eigenvalue. Here we are. Where's our Impala model? I think somewhere here. Is this it? Yeah. Yeah, so revisiting the Impala ranch, if we calculate the eigenvectors, we get an eigenvalues. One of the eigenvalues was 1.2, which is what we found, and the other is minus 0.4. So it's the 1.2, its eigenvector, which we found implies that x equals y, defines what's going to happen in the long run. And the other one, lambda equals minus 0.4, its eigenvector is x over y, x to y is proportional to minus 3. And it turns out that it's not going to have an influence in the long run of what's going to happen. It's the one that has the biggest absolute value of the eigenvalue. And so there's a lot of technical stuff here, but the takeaway message is if you have a matrix, you can find its eigenvectors and eigenvalues. The eigenvector and eigenvalue allow you to understand in the long run how that system is going to behave. How the system is going to behave is it's going to be controlled by the largest absolute value, eigenvalue, and its corresponding eigenvector. They'll determine the direction and the rate at which it grows. If the eigenvalue is negative, it's actually going to jump around because a negative times a negative is a positive times a positive is a negative. And for populations, that's not meaningful. For population models, what you'll find is that the largest eigenvalue is usually positive. Otherwise, there's something strange in that model. And the population will grow like that largest eigenvalue, which is positive. It'll determine the growth rate. And the corresponding eigenvector will determine what's called the stable structure, the stable ratios of the eigenvector. The stable ratios actually correspond in a population that has either an age or a stage structure to the stable stage structure. So in the Impala model, we had two stages, a juvenile and an adult. And the stable stage structure was 50% juveniles, 50% adults. In more complicated examples, and you'll see when we get to Leslie matrix theory in the next couple of lectures, is that if we've got 1-year-olds, 2-year-olds, 3-year-olds, up to 10-year-olds, then you can have a matrix model that tells you how the population changes in age in each time period. That model has a stable age distribution, and that tells you ultimately what proportion of individuals in the population will be in each age class. And it will grow according to its dominant eigenvalue, and the proportion in each age class will be determined by the eigenvector corresponding to that dominant eigenvalue. And that is called the stable age distribution. Or more generally, if we're not dealing with age classes but stage classes, then it's called the stable stage distribution. And this theorem tells you about this behavior in 2 dimensions, but it actually extrapolates to any dimension. And so you can look through these notes, but I'm not going to do any more mathematics per se on eigenvalues and eigenvectors and matrices. You need to just practice that yourself. But what we're going to go on to do is to talk about H-class models and how we can use them to study population growth and also how to manage fisheries where, for example, there's age structure in the fishery. Okay, thanks very much. Are there any questions?